Problem 3.11. It has two parts. Part A. By comparison with a classical oscillator, explain why the expectation values of x and px are both 0 for the quantum harmonic oscillator. Hence, show that delta x delta px equals square root of expectation of x squared times expectation of px squared for a quantum harmonic oscillator. Part B. Given that the average kinetic and potential energies of a harmonic oscillator are identical, prove equation 3.95. Now first let me write down this equation 3.95 before proceeding. So equation 3.95 states the following, that delta x delta px, the uncertainty product for a quantum harmonic oscillator, is the following: n plus half h cross, where n is the level of the wave function or the state in which the oscillator is in. Now this question is actually quite similar to the previous question that we did. We in fact very mathematically rigorously derived this expression. So if we go back and revise the previous question a little bit before proceeding to this question. So in the previous question we were given that the harmonic oscillator is in its ground state, and we had to find out this uncertainty product. And to find out the uncertainty product, we made use of this expression for the variances. The variances are defined as follows: expectation of operator squared minus square of the expectation of the operator. And in doing so, we also saw that the expectation of position turned out to be 0 over here, expectation value of position operator, and similarly expectation value of the momentum operator was also 0. And we did this very mathematically we saw, and it actually turned out to be 0 because the integral was an odd function in both the cases. Now the task in this question, okay, one more thing. So because the expectation of the position and momentum operators was 0, the in the uncertainties, the only terms which remained were the expectation of the operator squared. For px, expectation of px squared, and for position also what remained was expectation of x squared. So in that sense, delta x delta px product will actually be square root of x squared expectation times px squared expectation. So we actually did this derivation very mathematically. Okay, why is my screen shaking? Yeah, we actually did this derivation very mathematically, very rigorously in the previous question. So if you want to revise that, you can actually go back and revise this previous question once again. So how we did that was basically just evaluating the integrals. And in order to evaluate the integrals, we made properties such as integral of odd function is 0, product of an even and odd function is odd, product of an even and even function is even. Then we made use of the gamma functions and the Gaussian integrals, and putting it all together, we actually arrived at this expression that we are supposed to prove now in a more intuitive manner, and in a manner in which we actually compare with the classical case of the harmonic oscillator as well. So this is more like an intuitive approach rather than a very mathematically rigorous approach. So let us begin with part A. So classically, In classical oscillator, the particle oscillates about x equal to 0 and the position is given as follows, where x naught is the amplitude and t is the time, and this averages out to 0. Why? Because average value of sine function over a time period is actually equal to 0. And how this is true, we can actually plot the sine function and see it visually as well. So let me try and draw a sinusoid. So this is a sine function. So this is one time period t, this is t, and this is the sine function, sine omega t. And you can see that the portion, okay, let me use a different color maybe. The portion above the x-axis is exactly same as the portion below the x-axis. So as a result, these two parts cancel out. The area above the x-axis, or the time axis in this case, above the x-axis is same as the area below the x-axis. And so the area above the x-axis is actually it is positive, and below the x-axis, that is negative. So positive values are exactly same as the negative values, and so these two cancel out. Now let us look at momentum. For that we need to find out velocity. Velocity is nothing but derivative of position. Which is the following. Now momentum is mass times velocity, which is m omega x naught cos omega t. Now this also averages out to 0. Why? Because again the average of cos function over a time period t is also 0. And let me draw the cosine function. Okay, my axes are not even looking straight. Let me try again. Okay, this looks fine, and now I'll draw the cosine function. This is the cosine function over one time period. This is over one time period. This is the time axis, and this is cosine of omega t. And once again, you see that the part above the x-axis, these two segments, is exactly same as the part below the x-axis. This is positive, and below the x-axis is negative. So the positive part is exactly same as the negative part, and hence they cancel out upon integration. And mathematically, if I were to write it down, then mathematically the average value sin omega t, or equivalently cos omega t, is the following. 0 to time period, where t is 2 pi over omega. Similarly, for cos, instead of sine you will have cos omega t, and this actually the numerator turns out to be 0. So this is the mathematical way of writing it. Now let us look at the variances. So variances are given as follows. Because average value of x is 0, so it is just only the first term survives. Similarly, for the momentum, or since the entire motion is in the x direction, this is actually momentum in the x direction. Again, only the first term survives, and hence the uncertainty product is the following. So this was the more intuitive way of arriving at this expression for the classical harmonic oscillator, and then also for the quantum, generalizing it to the quantum harmonic oscillator. So generalizing it to the quantum harmonic oscillator would mean that these are operators and not just values. So for quantum case, these position and momentum values are simply replaced by their operator forms. Now we'll move to part B. So we know that the total energy, part B, in that we need to find out this uncertainty product for the non-ground state. Even for the excited states, n refers to the level or the state, n equal to 0 is the ground state. And we need to actually arrive at this expression by making use of the expressions for energies. Now energy, we know, is the sum of kinetic energy and potential energy terms, and this for the quantum harmonic oscillator we know is given as follows: n plus half h cross omega. Now the kinetic and potential energies, we are given that they are identical. So kinetic and potential energies, the average values are identical. So average values are identical, that is average of kinetic equals average of potential, and this means this is actually then equal to E over 2 from here, and then this is nothing but n plus half h cross omega by 2. Now the kinetic energy operator is nothing but p squared over 2m, that's kinetic energy, and potential energy is half m omega squared x squared. So the average value of kinetic energy is 1 by 2m average value of px squared, and average value of potential energy is half m omega squared average value of x squared. So this implies average value of px squared is 2m times average value of kinetic energy, and average value of x squared is 2 over m omega squared times average value of potential energy. Now let us take the product of average of position squared and momentum squared operators, this expression. So this is the following. We'll just make use of these two expressions. Now let's see what cancels out. M cancels out. Now average of kinetic and potential energies is nothing but E over 2 from here. So this 4 also cancels out. And again we'll make use of this expression of energy. Or rather, first let us look at the uncertainty product. So the uncertainty product is nothing but square root of the above. It is the square root of the following. This square root, which from the above is nothing but E over omega, and E is nothing but n plus half h cross omega over omega. So omega cancels out, giving us the desired result, n plus half h cross. So the uncertainty product for a quantum harmonic oscillator is delta x delta p equals n plus half h cross, and for the ground state it is the minimum uncertainty product, which is h cross by 2. And from Heisenberg's uncertainty principle, we know that delta x delta p should be greater than or equal to h cross by 2. And for special cases, it is actually indeed equal to the minimum value, that is h cross by 2, which in this case is for the ground state of the quantum harmonic oscillator. So this question was also once again on harmonic oscillators, and here we actually looked at the uncertainty product for quantum harmonic oscillators which are in the excited states as well, not just necessarily the ground state.